Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face Trending List, published on January 28, 2026, just yesterday. It shows that a new framework, called MathForge, can boost mathematical reasoning accuracy by nearly 5% on key benchmarks simply by targeting harder questions. The paper is titled, Harder is Better, Boosting Mathematical Reasoning via Difficulty-Aware GRPO and Multi-Aspect Question Reformulation. And as we'll see later, this strategy has some really promising implications for how we train reasoning models. And for those interested in the implementation, the authors have shared their code on GitHub. Table 1 compares the performance of various methods trained on the QN 2.5 Math 7b model. Starting with the standard Group Relative Policy Optimization, or GRPO baseline, we see an average score of roughly 37.6% across the benchmarks. The authors then test their components individually. The Difficulty-Aware Group Policy Optimization, or DGPO, alone lifts this to nearly 40%. Meanwhile, the Multi-Aspect Question Reformulation Strategy, or MQR, pushes it further to 41%. Finally, combining both into the full MathForge framework delivers the best result at roughly 42.2%, a significant 4.6% boost over the baseline. Table 3 now breaks down the algorithmic contributions within the Difficulty-Aware Group Policy Optimization method to pinpoint where the gains come from. The top section reveals that while basic loss averaging changes very little, adding the difficulty-balanced group advantage estimation provides a solid lift, raising the average score to about 38.7%. The performance peaks when we include question-level weighting in the full model, which reaches nearly 40%. Additionally, the bottom rows test the temperature hyperparameter, showing that a value of 2.0 creates the most effective distribution for prioritizing harder questions. Table 2 shows comparative performance results across different base models to test. Well, while the previous comparisons established the overall gains, Figure 1 illustrates the training dynamics behind them. On the left in Panel A, the accuracy reward for the difficulty-aware algorithm, shown in blue, climbs consistently higher than the baseline. This confirms a sustained improvement in learning. Then, looking at Panel B on the right, we see the response length. The blue line drops sharply here, indicating the model is learning to reason not just correctly, but more concisely by trimming redundant steps. So, moving on to Figure 2, we see the direct impact of using the harder, reformulated data during training. In Panel A on the left, the blue line represents the model trained on the multi-aspect question reformulation data, while the gray line tracks the original. Notice how the blue line stays lower here, which confirms that these reformulated questions are genuinely more difficult to learn. But looking at Panel B on the right, this difficulty pays off. When evaluated on the Unseen Math 500 benchmark, the blue line clearly outperforms the gray one, demonstrating that training on harder tasks builds much stronger generalization capabilities. To understand exactly which parts of the reformulation drive these results, Table 7 breaks down the strategies individually. The first two rows show the baselines, comparing the original data against metamath rephrasing, which sits around 40 to 41%. Next, the middle rows test the three specific difficulty-enhancing methods: adding background stories, introducing abstract terms, and nesting subproblems. While the subproblem strategy is the strongest standalone performer at about 41.5%, the bottom row reveals that the real power lies in combination. The full multi-aspect question reformulation approach achieves the highest average score of 42.2%, proving that diversifying difficulty across multiple dimensions works better than any single method alone. Wrapping up, the big takeaway is that systematically targeting harder questions improves mathematical reasoning far more effectively than just increasing data diversity. The results show that when we force models to tackle intrinsic difficulty, both through tougher data and smarter algorithms, their generalization capabilities jump significantly. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.